Hello and welcome to TechNights. My name is Shahul and I'm a second year PhD student in computational biology at CMU. In today's session, we'll be talking about different problems and what makes some of these problems harder than others. In particular, we'll be doing this through the lens of computational complexity theory. That is, if you have a computer, how much resources does the computer need to solve your problem? Now, that might sound very formal, but it's actually a very popular approach that can be used to understand problems ranging from solving video games to programming robots. So, with that in mind, after today's session, hopefully you'll have an idea of how to use complexity theory to think about what problems are actually worth spending time on. Before we get started though, make sure that you have the materials we need for the session. First, you'll need 4 printouts of the PDFs in the video description. Second, you'll need a computer with access to the internet. And third, you'll need a friend with whom you can play some of these games that we'll be discussing. So to begin with our discussion, let's look at some problems that are actually somewhat straightforward to solve. Although the problems that we'll solve in this section have pretty simple solutions, you might not be able to see what they are at the beginning. So by figuring out what those solutions are, we'll get a better intuition for why they're easy problems. Our first game is Hot Potato. How can you play Hot Potato so you don't lose? I'm sure many of you have heard of Hot Potato before, but probably never played it with a real potato. So I'll explain the basics of the game and introduce a few new rules so we can analyze it much more easily. So the basics of the game are pretty simple. Basically, there's a hot potato with a timer on it, and 2 players pass the potato between each other. And whoever is holding the potato when the timer runs out loses because the potato explodes all over them. And nobody likes that. But we're going to add a second rule, which is when you receive the potato, you have to hold on to it for at least 1 second before handing it off to the next player. And the question is, how can you play with this new rule in order to win? Well, it turns out it's pretty simple with our new rule. So if there's n seconds left on the clock when you receive the potato, just wait for n minus 1 seconds. And then your opponent will only have 1 second left when they receive the potato. And because that rule means that they have to wait for at least 1 second, that means they'll be holding a potato when it explodes, and they will lose. Therefore, you will win. So it turns out that this is a winning strategy, which will always work for the first player. And that means that this game is kind of boring, because the second player can never win. So let's introduce another rule to make our game more interesting. Now, instead of waiting forever, the player can only wait between 1 and 2 seconds before passing it off to the next player. We'll call this game Limited Hot Potato, because the amount of time you can wait is now limited. So the question is the same: how can you play to win Limited Hot Potato? And is there even a winning strategy which will let the first player win all the time? Well, it turns out there is a way to figure out if you can win or not. So let's see if we can figure out what that is. Well, if you think about it, the only thing that matters in this game is how much time you have when you receive the potato. Based on that, you should be able to figure out if you can win or not. So let's say we have a magic tool called Can Win. On the slides, this is indicated by a black box. And this function, our tool, can tell us whether a player can win, given just the time. So clearly, if we know how this tool works, we can use it to our advantage to win the game. So let's make this more concrete. What should the output of Can Win be when there's 1 second left on the clock? Well, it should be no, because if there's only 1 second left, then you have to wait for 1 second and you will definitely lose because the time will run out at that time. So the answer is no, you can't win if you receive the potato with 1 second left. But what about if you have 2 seconds left? Well, you know that if your opponent gets the potato when there's only 1 second left, they will definitely lose. So why don't we just wait 1 second and then give the potato to our opponent? In that case, they will definitely lose, which means we will definitely win. So for 2 seconds, the answer is yes, you can definitely win. And how about 3 seconds? It turns out you can do the same thing because you can wait up to 2 seconds, the maximum time, at which point your opponent will receive the potato when there's only 1 second left. and they will lose and you will win. So the answer for 2 and 3 seconds is yes. Now, what do we do if there's 4 seconds left? What's the answer? Well, you have a couple options. You could wait 1 second or 2 seconds. But in either case, your opponent can win based on what we've just calculated, right? Can win for 2 seconds and can win for 3 seconds is equal to yes. So, because we can't go to any position other than one in which our opponent will win, can win for 4 seconds is no. That is, our only option is to hand the opponent a win. Now, we can visualize these 4 time steps and the logic that we just described with this simple graph on this slide. Here, the numbers represent the amount of time left, and the colors represent whether you can win or not at that amount of time left. So here, red is you cannot win, and green is you can definitely win. So notice that there's actually a pattern, and if I draw some arrows, you can see what that is. Basically, if you can win at a certain time, it depends on whether you can win or not at the 2 time steps that are before that time step. So there's actually a pattern here. If we continue up to 10 seconds, we see that there's a repeating block of 3, which consists of every losing state followed by 2 winning states. The arrows that show the dependencies between these blocks kind of prove that the pattern continues forever, even past 10 seconds. So how can we summarize this pattern? Well, notice that every losing state is 1 more than a number that is divisible by 3. So to describe that, we're going to introduce a function called the modulus operator. It's just a percent sign, and what it means is if you have a mod b, then you take a divided by b, and whatever the remainder is the output of the mod operator. So for example, 3 mod 3 is 0, because 3 is exactly divisible by itself. However, 4 mod 3 is 1, 5 mod 3 is 2, and then 6 mod 3 is again 0, because 6 is exactly divisible by 3. Now, with the modulus operator, we can exactly describe how the can-win tool works. Basically, if the amount of time left mod 3 is equal to 1, then you are guaranteed to lose. Otherwise, you can definitely win. So the strategy for us to play the game is when you receive the potato, wait enough seconds until the amount of time left mod 3 is equal to 1, and then hand it off to the next player. If you can do this, then you win. Otherwise, you lose. Alright, let's move on to another problem. Suppose that you and your friend decide to split a chocolate bar with each other, and the chocolate bar is split into sections of predetermined lengths. Here's an example on the screen, with the length of each section in terms of millimeters. The two of you decide to play a game in which you break off chunks of chocolate and eat them. There's a rule, though, that you can only take chunks from the front or the end of the bar and not from the middle. So in each player's turn, they can take either the front chunk or the back chunk. However, there's a catch. Since you're the better friend, you want to make sure that your friend eats more chocolate than you. So how can you play the game to make sure that you eat less chocolate than your friend? And of course, they're trying to do the same thing, so you have an adversary in that respect. We'll call this problem the chocolate splitting problem. And here's the full description of it. Notice that we guarantee that the number of chunks in the chocolate bar is even at the beginning. So, how can we solve this problem? Well, let's begin by numbering the chunks of the chocolate bar from left to right. In this example, we number 4 chunks, since that's how many the bar starts with. Now, with this numbering in mind, this is the strategy as follows. Add together the lengths of the odd numbered chunks, and separately add together the lengths of the even numbered chunks. If the sum of the odd numbered chunk lengths is smaller, then we'll always pick odd numbered chunks when we get the chance. Otherwise, if the even numbered sum is smaller, we'll just pick the even numbered chunks. This strategy, it turns out, is guaranteed to make sure that you eat less chocolate than your friend. So to see that, let's use this strategy on our example from before. If we take the sum of the odd numbered positions, which is 8 millimeters and 3 millimeters, we get 11. If we take the sum of the even numbered positions, we get 15 plus 7, which is 22. Now, since 11 is less than 22, we're going to pick the odd numbered positions. So notice, if we pick the chunk in the first position on our first turn, then in the next turn, the opponent can only pick even positions. Vice versa, if we pick the last chunk, then our opponent only has the option to pick odd numbered chunks in their turn. So in that way, the first player controls which chunks, either even or odd, the other player will get. And so the first player can always pick chocolate such that they win. So let's see this play out for our example. Since we're the first player, and we know that the sum of the odd number chunks is smaller, we'll take the first chunk. P1 takes the 8mm chunk. That's us. Next, P2 will take the last chunk, which is 7mm. And then we will take the third chunk, 3mm. And finally, P2 has to take 15mm. Here we get 11, and they get 22mm, meaning that we were the better friend. Alright, great. So, in some sense, the problems that we just finished discussing are not too difficult to solve. We saw that for problems like limited hot potato, it's possible to solve them with a simple rule. Just divide one number by another. For chocolate splitting, all we had to do was take the sum of a bunch of numbers, and that shouldn't be too hard to do. But now, let's look at a problem that's a bit different from the ones we've talked about so far. Tetris. You've probably heard of Tetris before, but if not, it looks something like this. It's one of the most popular video games of all time, and the basics of the game are as follows. There's an infinite stream of blocks falling from the top of the screen, and you have to organize them in rows as they fall. When you complete a row of blocks, that row gets removed from the screen, giving you more room to play with. However, if the blocks stack up and reach the top of the screen, then you lose. Also, you get lots of points if you manage to get rid of all the blocks on the screen for a brief period of time. It's a lot easier to understand if you just play the game, so try it out at the link on the screen. Here's a clip of me playing and trying to survive as long as I can. So as you can tell, this game can get pretty hard pretty quick. One question we might have is, how can we think about how hard Tetris is, just like we did for the other two games? Well, one objective in Tetris is clearing the board of all pieces, just for a brief moment of time. This is called a clear, and as I said before, this gives you a lot of points. So it seems like a good goal to achieve. So we'll call this problem TETRIS-CLEAR, and it's described in full here. The problem statement is essentially, is it possible to clear the board in a set number of turns? Now, how does TETRIS-CLEAR compare to the previous problems? Well, compared to chocolate splitting, it's actually pretty hard. In chocolate splitting, all we had to do to figure out the right answer is add a bunch of numbers together. But for TETRIS-CLEAR, it's not that simple. For each Tetris piece that we get, there are so many options on where we can put the piece, and we can even rotate it before it settles down in the game board. In addition, the spots in which it can go actually depend on how we placed all of the previous blocks. So there's obviously a lot of complexity in Tetris, and that makes it harder than chocolate splitting. Alright, let's move on to another problem. And this one is not a game, but rather a fun pastime. Origami. If you haven't heard about origami before, well, first of all, I recommend you try it because it's a lot of fun. But basically, it's the art of folding paper into intricate designs, such as the elephant you can see in this time lapse. One thing to notice about the paper that's being folded is that before it folds into a 3D elephant, it's actually lying flat on the table. This indicates that an important part of folding origami designs is folding it up so that it lies flat before you assemble it in the final position. If we unfold the elephant and look at the creases of the paper that were made, we'll see that folding origami is just a question of folding the creases on the paper correctly to get the final design. In the diagram, the red lines indicate mountain folds, where the creases pop up towards you, whereas the blue lines indicate valley folds, where the creases pop down away from you. If you fold a square paper along these lines and in the correct mountain-valley orientations, you will for sure get the elephant. One thing to notice, though, is that in many places of the crease pattern, there are a bunch of creases that meet at a single point or vertex on the paper. In order to create a piece of origami that lies flat on the table, we need to fold these creases in such a way that, after folding, the design will still be flat. So this leads us to the idea of flat foldability. Let's say you have a bunch of creases that go into a single point. Then, we want to fold these creases such that the whole paper at the end lies flat on the table. If you can do this, we say the paper and the point is flat foldable. In the picture on this slide, there are 8 creases going into the center point, and it is indeed possible to fold them such that the final origami lies flat on the table. Now we have what we need to make the folding origami problem concrete. Let's say that we have a crease pattern with a bunch of creases going into a vertex. Our question is this: is it possible to orient the creases, either make them mountain folds, valley folds, or not take the crease at all, such that the folded design lies flat on a table? If so, we say that the design is flat foldable. So we'll call this problem flat folding. Before we do anything else with the origami though, let's go through some real examples. Look at the 4 PDFs that you printed out. On each of them you'll see a set of lines. For each PDF, fold the paper over these back and forth, as shown in this clip here. This process is called pre-creasing and will help us fold the papers in the next steps. Note that it might take you a while. This ended up taking me a full 10 minutes, so don't worry if it takes you some time. Alright, so for our first flat folding puzzle, we'll take the example with all 90-degree angles. My question to you is this: is it possible to flat fold the paper? I'll give you a few seconds to think about it, but feel free to pause the video and try it yourself. Okay, so the answer is yes, you can. And I'll show you how. Basically, you choose one of the edges to be a valley fold, and you choose 3 of them to be mountain folds. If you fold this up, it lies flat on a table. Here I've colored the edges to demonstrate this solution. Now let's look at the next example. This is the one with 105 degrees, 150 degrees, 60 degrees, and 45 degrees. I'll ask you the same question: is it possible to flat fold this one? The answer to this one is probably less obvious than the first one. However, if I try to fold along these lines, it should become obvious that there's no way to physically do this without the paper popping up. And you can see in this clip that I try to do it for a while, but I just can't. If you were to try every combination of possible fold orientations, which I didn't exactly do, you would see that no combination will possibly lie flat. So, there's no solution. Now, let's look at a third example. Again, the question is it possible to flat fold this? The answer to this one also might not be obvious at first, so you can pause the video and give it a try. It turns out that it is possible to flat fold this design, as I'm doing in this clip here. In this solution, we mountain folded 3 of the creases, valley folded 1 of them, and left another uncreased. And you can see this on the slide. Alright, so at this point you might be wondering if it's possible to figure out whether you can flat fold a vertex or not without actually folding it up. And it turns out that there is a simple rule which will help you figure this out. If the angles that are implied by the creases at a vertex can be split into 2 groups that add up to 180 degrees, then yes, you can flat fold a vertex. If that's not possible, then no, you can't. So to see why this is true, let's look at the solution for puzzle 3 in particular. In this slide, I've colored the sections of the paper that lie between each two creases by the direction in which they face when the design is folded flat. The blue sections face up, and the orange sections face down. With this coloring, we can see that the sum of the orange angles is 180 degrees. Intuitively, the sum of the blue and orange angles must both be 180 degrees, because the creases go in a circle around the vertex, so that the angles that go in the blue direction must cancel out with the angles that go in the orange direction, in order for us to start and end at the same place. Great, so now you know the trick. Here's one last puzzle. Is it possible to flat fold this design? I won't actually tell you the answer to this one, so try and figure it out by yourself. Hopefully you can see from these hands-on examples that flat folding and origami in general is not that straightforward. Now let's move on to the next problem. I know it seems like we're doing lots of problems, but as you will soon see, this problem has a very deep connection to flat folding. So the problem is as follows. Given a set of numbers, can we split them into two subsets that have the same sum? So in this example on the screen, our list of numbers that we're given is 1, 2, 2, 2, and 5. And it turns out we can split this into two sets, 1 and 5, and 2, 2, 2, both of which sum to 6. Therefore, the answer for this case is yes, we can split it up as we want. Now, what I want to convince you of is that the two partition problem is actually pretty hard. For the example we just saw with 5 numbers, it didn't seem too hard. But what if instead we had 50 numbers, like in this slide here? Can you figure out a way to two partition this set of numbers? Or if it's not possible, can you tell me that it's not possible? You can probably see that there's many ways in which you can split up the numbers to try and see if they add up to two subsets with the same sum. But it's not clear where to start or how long it would take to even try this. Now, it turns out that's actually possible to split the numbers up into two groups with the same sum. And I've done that in this slide. You can see that the areas of the rectangles are the same. However, how long do you think it would take for you to figure this out if you didn't know the solution? Probably a really, really long time, because you'd have to try out lots of different combinations. Okay, so since I didn't want to try and solve this particular problem every time by myself, I wrote a computer program that solves two partition for me. The program takes in a list of numbers and figures out if it's possible to split them up into two groups with the same sum. And in this graph, I plotted how much time it takes my program to run given the size of the list of numbers that I give it to it. As you can see, there are some ups and downs in the graph, but overall the runtime of my program gets larger and larger as the list of numbers gets longer and longer. And also, the rate at which it gets larger keeps growing. So it's really, really not easy. You can imagine if I have 1,000 integers in my list, then the runtime of this program will get really, really big. Now, as I said before, it turns out that the two partition problem is very strongly related to flat folding. To understand how, we first need an idea called a reduction. Basically, a reduction is a procedure by which you show that one problem is at least as hard as another. Because if you can solve this problem, then you can solve the other problem. So I'll give you a practical example. Let's say that you're at the grocery store and you want to buy an onion. The grocery store sells onions in two quantities, either a single onion or a bag of 100 onions. You don't yet know the exact cost of a single onion, but somehow you know that a bag of 100 onions costs $200. So the question is, can we use that information to reason about the cost of a single onion? Now, here's where the reduction part comes in. So suppose you didn't know the price of a 100 onion bag either. However, one way to get 100 onions is to just buy a single onion 100 times, right? So in order to figure out how much 100 onions would cost, you can just figure out how much a single onion costs and then multiply that by 100. So let's say we have a way of figuring that out. For example, maybe the manager of the grocery store can just tell us how much a single onion costs. That magic way of figuring it out is indicated by a black box on the slide. Once you figure out that price, X, you just multiply it by 100, and that's your guess of how much 100 onions costs. Now, since you know that 100 onions cost $200, and this could be cheaper than buying 100 single onions, because buying things in bulk is always cheaper than buying them one by one, then you know that 100 times X has to be greater than 200. Therefore, the price of a single onion has to be at least $2. In this way, we can say that buying 100 onions reduces to buying a single onion. And if we know how much a single onion costs, we know how much 100 onions could cost. Okay, now this is where it gets really exciting. So it turns out that we can reduce the two-partition problem to an instance of the flat folding problem. That is, we can convert our two-partition problem into an origami crease pattern, so that if it's possible to fold the origami crease pattern, then we know that it's possible to split the list of numbers into two groups. To see how to do this, let's walk through the process for our previous example of 5 numbers. First of all, notice that the sum of the numbers is 12. 2 plus 1 plus 2 plus 2 plus 5 is 12. Next, notice that there's 360 degrees in a circle, and all of the creases that go around a vertex form a circle. Finally, 360 divided by 12 is 30 degrees. So this is an important scaling factor that we'll use to define the angles in our origami crease pattern. So in this slide, we see that we can translate each of the numbers in our list into angles that go around a circle. We just multiply them by the scaling factor that we just derived. So for 2, the corresponding angle would be 60 degrees. For 1, it would be 30 degrees. And for 5, it would be 150 degrees. So we've converted our original list of numbers into angles in an origami crease pattern. Now, what have we accomplished by doing this? Well, if we can flat fold these angles, we know that we can partition our numbers. And conversely, if we cannot flat fold these angles, then we cannot partition our numbers. So here's a diagram that shows that to be true. Here, the original numbers are marked in red, and they're placed on top of the angles that they correspond to. You'll notice that this turns out to be exactly the same as puzzle 3 in the flat folding puzzles that we did. And if you'll remember, that puzzle was solvable. And in the same way, the 5 numbers that we have here are also partitionable into 2 sets that add up to the same sum. So we have a yes for both problems, which is exactly what we wanted. Here's a flowchart that explains the logic that's going on here. Basically, if there's a magic tool, indicated by a black box here, to solve flat folding, then we can use that same tool to solve two-partition problems as well. So we've effectively shown that solving the flat folding problem is just as hard as solving the two-partition problem, because if we could solve the flat folding problem, we could always solve the two-partition problem in the same way. Alright, finally, we move on to our last activity for the session. Now, the game we're going to describe here might seem simple at first glance, but it turns out it's actually pretty hard. It's called Geography or Word Chain, and it's another 2-player game. You start by choosing a category, for example, countries of the world, and picking a random word from that category. The first player has to pick another country that has the first letter that's the same as the last letter of the starting word. The second player has to continue the pattern, that is, pick another country such that the first letter is the same as the last letter of the last country. However, they have to pick a country that hasn't been used yet. The players will keep alternating in this way until there's a country that has no new destination. That is, there's no country that hasn't been visited yet, which will satisfy the first letter, last letter constraint. So here's the full description of the game. To get a better feel for the game, you can go to the link on the slide and play it with a friend. If you do play it with a friend, try to see if you can make it so that your friend loses and you win. An example run of the game might look like the picture on the screen. Here, the red lines indicate the path the 2 players have taken so far, and the gray lines indicate paths that are no longer valid because they visit old countries. Alright, so now we're going to try to put it all together. So today we've talked about a bunch of different problems and games, ranging from puzzles to video games, and even including origami. We saw that some of these problems can be considered easy and some are definitely hard, and we thought of different ways to measure this. We even saw that it's possible to reduce some problems, such as flat folding, to other problems, like two partition, to show that they're equally difficult. Now we might ask in general, how can we compare problems? We can't always come up with reductions, can we? One of the most common approaches to this is to consider if you had a computer to help you solve the problem, what is the minimum amount of resources the computer would need to do it for you? Well, in general, we consider two resources that a computer might need. One is time. Some problems just cannot be solved in a small amount of time, and those problems are considered to have high time complexity. Alternatively, sometimes a computer needs a lot of space or memory in order to solve a problem. Those problems that require a lot of space have high space complexity. Here are two categories of time complexity. The first is polynomial time, or just P for short. These are problems that can be solved in an amount of time that is polynomial with respect to the size of the input. If you don't know what that means, it just means that those problems can be solved very quickly. And the second category is non-deterministic polynomial time, or just NP for short. For these problems, although it might not be possible to solve them in polynomial time, it's possible to check their solutions in polynomial time. Here's some examples from the problems we discussed today. The chocolate splitting problem can be solved just by taking the sums of the odd and even numbers alternately, and therefore it can be solved in polynomial time. On the other hand, for flat folding, if someone tells us an assignment of the edges, that is either mountain, valley, or not taken for each of the edges, we can check if this produces a flat folding origami design just by trying each of those orientations of the folds and seeing if the folded thing lies flat on a table. That is, we can check a solution very quickly. For space complexity, the most important category of problems is polynomial space, or just P space for short. These problems can be solved by a computer using just a small amount of memory. Great, now with these definitions, we can draw a Venn diagram that shows how these categories relate to each other. Here I place the three problem categories that we just described. You'll notice that any problem that's in P is also in NP, and any problem that's in NP is also in P space. This implies a hierarchy. That is, if a problem is in P, it's easier than problems that are in NP but not P. So now the obvious question is, how do all the problems that we talked about today fit into this Venn diagram? Well, I'll show you. Here's the complete diagram. We already talked about chocolate splitting being in P and origami folding being in NP, but you can see where the rest of the problems fit in as well. You can start to see the hierarchy very clearly now, and it makes some sense. TETRIS-CLEAR is above chocolate splitting in the hierarchy, and this confirms what we think about how hard TETRIS-CLEAR is versus how hard chocolate splitting is. However, there's a catch to the illustration that I have here, which is that we're not sure whether all these problem categories are the same or not. That is, it's possible that if a problem is in NP, it must also be in P, and the same for P-space problems. So another way of phrasing this question is P equal to NP? Here that's indicated by these question marks in blue boxes. And similarly, is NP equal to P-space? If P equals NP is true, then all the problems we've talked about today are actually equally as hard as each other. This seems unlikely, but no one has actually been able to prove or disprove that P is equal to NP. It's a really hard problem, and in fact, it's so important, it's been labeled as one of the Millennium Prize problems. That is, if you solve this problem, you'll get $1 million prize. So clearly it's not an easy thing to solve. So today's session was all about thinking about different problems, what makes them easy or hard, and how to compare them to each other. But why is this useful? Well, first of all, we saw that with reductions, we can solve new problems using solutions to old ones, if we know how to solve those old ones. So this can save us a lot of time and headache when we're faced with problems we haven't seen before. Second of all, let's say you know that a problem is really hard. Then you know when you're done working on it. For example, if you're trying to write a piece of code to solve a problem, and your code is inefficient, that might just be because the problem cannot be solved any faster than you have written your code. And that's when you know you can stop working on it and move on to the next project. And finally, it's important to understand the relationship between classes of problems. For example, in modern cryptography, which is used to send any secret information over the internet, such as your bank account information, there's a reliance on the NP-hard problem of prime factorization. If someone shows that P is equal to NP, this means that prime factorization is actually easier than we think, and it could be a lot easier to hack someone's bank account information or private information. So that's the end of this week's session. Hopefully by thinking about these problems, you have a better idea of how to solve other problems or tasks that show up in your life. And perhaps you even know when a problem is just too hard to solve. Thanks for watching. Bye.